Okay, welcome back. So we've been talking about these two-layer neural networks. And here we have the basic construction of one. So we start with some vector, typically vector input. That goes through an affine linear transform to give us these outputs z. Each z as a scalar goes through a nonlinear activation function. And the outputs of these, that's the output of the hidden layer. They now go into the output layer. And the output layer is basically just something like logistic regression or linear regression. We can think of these as the transformed features. In any case, these features go through another affine linear transform to produce these outputs. Sometimes we call these scores or logits in the context of classification. And then we go through an optional nonlinear layer at the output. And last time we discussed the choice of activation. We discussed a little bit about how many of these hidden layer neurons to include, and we talked about why we don't typically need to have a nonlinear activation there, but if we do, we have to choose it carefully. It has to match the task. And so we saw these are some of the choices of hidden layer activations. We talked about output layer activations, logistic sigmoids, softmax. And we talked about loss functions for training. So these are the standard ones that we've seen, although there's a lot of flexibility here. So if we're doing binary classification, we would use binary cross entropy. But we have to be careful whether we define that loss in terms of the linear outputs of the last layer or in terms of the sigmoid outputs. And then for multi-class classification, the standard thing to do is, again, cross entropy. But once again, we have to make a distinction between whether we are defining the loss based on the linear outputs of the last layer or on the softmax outputs. And then for regression, popular loss would be L2 loss, but you could also use L1 loss or something like that. Okay, and then we talked a bit about gradient descent. And we remarked that for a lot of these neural network applications, you have very large training sets. So when you form the cost or loss function, it is the average of many per element causes or losts. And so when you do gradient descent and you look at the gradient term, you see that the gradient term is also like a scaled average of individual gradients for all those elements. And so if n is very large and you implement things in this standard way, it can be very expensive to compute every single gradient descent update, and you may have many, many of these updates, thousands, millions. But if you think about it, since we know that gradient descent doesn't even point us directly towards the solution, it just takes us downhill, which is hopefully in the right direction. Essentially, we don't have to worry about computing this exactly. As long as we compute, as long as we approximate this with some version of it that is correct on average, we can still use this same approach. And that is what we do here using what are called mini batches, and that gives us the stochastic gradient descent algorithm. So the idea with mini batches is that you have, let's say, your whole training set where every one of the rows of this matrix would be a sample. So a mini batch would be a chunk of samples, maybe on the order of like 32 or 64 or something. And so what you do is you approximate the gradient. Instead of using an average over all the samples in your data set, now you just use the samples in your mini batch. And then you perform a gradient descent in the standard way, except you're using this gradient approximation. and this is called stochastic gradient descent. Okay, any questions so far? Okay, and then we did a little bit of analysis of stochastic gradient descent. We looked at the expected value of the gradient. The reason why the gradient is random in this case is because we are drawing a subset of indices that defines this mini batch at random. And so we can look at what happens when we take the statistical mean over that random set of indices. And we find that basically we get back the gradient. And so essentially that means that our stochastic gradient is the true gradient plus some gradient noise that is zero mean. So when we use this stochastic gradient descent algorithm, instead of taking a smooth trajectory downhill, we take a noisy trajectory, but on average, it still follows exactly the smooth trajectory. That does give us one additional issue, is that when you get close to the stationary point, you will never settle down at that stationary point if you have a fixed step size, because you will, even if you, let's say, initialize the algorithm at the fixed point, when you use a mini batch, the gradient is not going to be exactly zero, so it's going to kick you off the solution, and you will just keep bouncing around. Okay, so what you have to do to counter that is you may want to reduce your step size. If you reduce your step size, essentially it's kind of like what happens is all these random perturbations get averaged, and you have less noise at the cost of taking smaller steps or taking longer to converge. But again, there's a trade-off, because as your mini batch gets smaller, the work to compute each step gets smaller too. So yeah, so there's basically for any choice of the mini batch size, there's going to be kind of an optimal step size that is going to be not too big and not too small. So those things have to be chosen together. All right, so this is stochastic gradient descent. I think this is as far as we got last time. Any questions so far? Is this making sense, how we're doing it? Okay. So here's just some implementation details and a few important definitions. So as always, we say that we have n samples in our training data set. And now, as a new variable, let's say that we have b samples in each of our mini batch. So, we said maybe b is on the order of like 32 or some number like that. So if you now say, well, how many mini batches will I need to cover my entire training data set? That's going to be this number. You have to take the ratio n over b, which may not be an integer. And then if it's not an integer, you have to round up. So if n is not divisible by b, what that means is that the very last mini batch you draw will be of size smaller than b. So for example, if you had, if you had a mini batch of 2 and you had 3 samples in your data set, the first mini batch would have 2 samples, and then there would be only 1 sample left, so the last mini batch would just have that remaining sample. Okay, so that's why we have, this is like round up. That's what those brackets mean. Okay, so B samples in a mini batch. T is the number of mini batches needed to cover the entire training data set. And we're going to run one stochastic gradient descent iteration per mini batch. So that means that if we go through and draw samples out of our training set to make mini batches, it will take us T stochastic gradient descent iterations to process all of our training data. And this number T is called a training epoch. It's how many iterations you need to make your way all the way through your training data. So rather than doing it like completely random as suggested maybe here, what's actually done is more like what's in this picture. So you shuffle your entire training data set, and then you, on this shuffle data set, you pull out mini batches sequentially. Like that would be maybe your first one, this is your second one, this is your third one, and so on until you make your way to the end. In doing that, you will have used capital T iterations of SGD. Now, and that's one epoch. Now you begin the second epoch. You reshuffle your training set, so use a different random seed, and now you're gonna, once again, take out the first mini batch, one SGD update, the next mini batch, another SGD update, and so on. And you often measure how much processing based on how many epochs you've done, not how many iterations. You say like, you know, I trained with 10 epochs, meaning I went through my training data 10 times with these mini batches until I said I was done converging. So that's the idea, and that is described here. You repeat this for each training epoch. You randomly partition your training indices into T mini batches using a different random seed for each epoch. And then you go through each one of those. Basically, this is like the algorithm here. For the training iterations, sorry. So we have T mini batches, yes. So for each mini batch then, we use any mini batch indexed by little t, we use IT, those indices, to perform the SGD update. Okay, so this is basically how we do it. And the nice thing is that all of this stuff is done for us with different frameworks for training neural networks. You don't have to do all the bookkeeping and all that stuff. In the old days, if you were working on this stuff, I don't know, more than 10 years ago, you would have had to code everything yourself, but then nowadays there's nice implementations where it does all this for you. And we'll go over that next time. Okay, so this is mini batch stochastic gradient descent. Is it clear how it's set up? Any questions? Okay. All right, so so basically, coming back to our overall problem we're trying to solve, which is how do we train this network? So we said these are our training parameters. We have the hidden layer, weights and biases, and then we have the output layer, weights and biases. We have to learn all those things. And we said we're going to use mini batch stochastic gradient descent, which has this form. So this is the average over the samples in the TEEF mini batch of the per sample gradients. And here we have our step size, which might be changing across our iterations, and then everything else is just the gradient descent update. So the key question now is, how do we compute this term here? This is the gradient. And this gradient is actually going to be dependent not only on the parameters, but also on the iteration t, because you're using, even if you had the same parameters, at different t, you're using different subsets, different mini batches. So that's why we have this extra notation on the cost or the loss. Okay, so the question now is, how do we actually compute this quantity? This is, we have done a little bit of this stuff in Unit 6 when we looked at exactly how do we code things for logistic regression, and now we have a little bit more complicated problem because we have these nonlinearities and a more complicated predictor function, a neural network. So for for the model we're looking at now, this 2-layer MLP, these are all the things we need to compute. So we need to compute the partial derivative with respect to each one of the coefficients in the hidden weight matrix, this one. Right? And there's basically, this is a 2D array, so we can index those coefficients according to the Lth row and the jth column. So we have to compute this scalar gradient for all L and J, or the scalar derivative. Okay, and then we have something similar here, except this is a one-dimensional quantity, so we have to compute the partial derivative for each entry in the BH matrix. And then for the output weights, that could also be a matrix. So here we have the partial derivative with respect to the kth row and Lth column of that matrix, and then we also have partial derivative with respect to those entries. So these are all the things we need to compute, and that's what we're going to do. We're going to spend a few slides going through and slowly learning exactly how to do that. And just to make the notation cleaner, we are going to omit all the t variables because essentially we're just going to focus on one particular iteration t, so there's no point in showing t on all the slides, and that will clean things up a bunch. All right, so that's what we're doing next. And to understand and organize this in our minds, we're going to use something called the computation graph. And basically, this thing is just showing us which variables depend on which other variables and how. Not exactly how, but just like which ones depend on which other ones. And the main point in doing this is using this graph, we can visualize how we're going to compute things in our network. So essentially, there's two stages of computation. There's the forward pass and the backward pass. The forward pass is pretty straightforward. It talks about how the data flows through this network from left to right, essentially. And the culmination, so what's happening in the forward pass is you're at the beginning of a stochastic gradient descent update. So what you know are the parameters from your previous update. So these are known quantities. Then you have some data, which is coming in. So the X and Y would be the features and the labels. And I is indexing the samples in the mini batch. So these curly braces mean there's actually a set of different X's. So in particular, we could think of this as X1 all the way to XB when we have B samples in our mini batch. Right, so I'm just writing the curly braces like that as an abbreviation. So in other words, we don't have mini batches of the weights, right? We just have the hidden weights, hidden biases, but we do have a mini batch of features, and we have a mini batch of corresponding targets. Okay, so based on the equations that we've seen before, which are summarized here, given these features, the very first thing that I can compute is I can use the hidden weights and biases and the features to compute the linear output in the hidden layer, these guys, for all samples in the mini batch. Okay, so the data kind of starts here and flows through, and now we compute these. So now these things are known to us. Now that they are known, we can compute these activations just by putting those linear scores through our hidden layer activations, and now we get the activations themselves here. Now that those are available to us, we can compute the outputs of the output linear layer. So we put these through this matrix and add the biases, and we get our output linear scores here. And finally, the output linear scores and our labels, those are the things that we can use to compute the loss per sample, and then we can sum over the batch, the mini batch, to get the final scalar loss that describes the entire mini batch. Okay, so this is the forward pass, starting with what we know and sequentially moving our way through computations until we finally get the loss. Okay, everybody clear on the forward pass? Okay. So to understand the backward pass, we're going to kind of first review the chain rule, and then we'll look at a very simple case, and then we'll move our way through more complicated cases. So just to remember, what is the chain rule? So here's a simple computation graph where z depends on y and y depends on x. And this is just some generic functions take x to y and y to z. So if you want to compute dz dx, you can compute that by computing dz dy and multiplying that times dy dx, right? This is just the chain rule of calculus. Now, let's suppose that we insert another variable into our network, and maybe this is just like another way of describing things where this was sort of like an intermediate variable between here and here that we didn't actually define here, but now we defined it. And so we have essentially the same processing steps, but we just have this sort of intermediate variable that's named in this case. So we can use the same technique. If I want to do dz dx, well, one way to do it is I can do dz du times du dy times dy dx. And I can multiply those things together to get dz dx. But because these are equivalent, now we realize that if we don't want to involve this in our computations, we don't have to. So if I want to do dz dx, I can choose to do dz dy times dy dx if that's more convenient. So I'm just sort of like taking this in one big jump rather than breaking it into smaller sections. Okay, so keep that in mind. So this is all in the case where these are all scalars, and the computation graph looks like that. Now, as we know, in our neural network training, we often have the case where there's several variables together at one of these nodes, or maybe it's because we have several variables in a mini batch, or maybe it's because this is a vector valued quantity. So in that case, we have a picture like this, and so when I'm writing the curly braces here, I'm really saying that there's actually a collection of variables here. So maybe a better way to picture that would be to draw some additional nodes, like a stack of nodes. And now recall that the data is really flowing through like this. Okay, so that's what I mean with this curly brace. It's like there's actually several variables here. And to go from x to u, in general, you may be going through each of those separately. Okay, and in that case, we have talked about the multivariable chain rule, and we've actually drawn this little diagram before too, but it explains why this is how you have to do things. So I guess the way that I did it here is I'm doing dz dyi directly. So I'm doing this for each of them. So that's what these terms are. So if I want to do dz dx, I do dz dyi directly times dy dx, but then I have to sum over all the y's. And that's how we get this expression. Okay, yes?
If there's an intermediate dependency on you skip you, like computation. Like I get that I understand you just removing dz dy by like the two individual components, but like in practice, aren't you still computing the derivative with respect to you anyways? Because if you didn't, then it would just get left in.
I'm not sure what you're asking exactly, but
Like, just because you can group them together doesn't mean that the actual, like, isn't the actual computation still dealing with you?
yeah, exactly. It is. That's right. That's right. So like here, like let's say that, just for example, like z is a cosine of 2y, right? So I can do dz dy directly, or I could say z is cosine of u, and u is 2y. Right? So I could break things up by dividing that intermediate variable, but I don't necessarily need to. And if I can, or let's say if I've already computed dz dy, then I can kind of ignore this way of breaking things up. So that's my point. Yeah. But yes, like mathematically, they're the same. You have to take into account the exact functional relationship between z and y. We're not making any approximations. Okay, great. All right, is everybody with me so far? So these are the things to keep in mind. And so now what we're going to do is we're going to go through the backward pass, also known as, the backward pass for, also known as back propagation, for a simple version of our two-layer MLP, where all the variables are scalar, and we have a batch containing only one element. So we don't, so this, you can see like this was the full case here where I had batches of several B elements. So now I'm saying, forget the curly braces because there's just one element there. And I'm also saying, these are not vectors, these are all scalars. So that's gonna simplify things quite a bit. So now we just have a scalar variable at each node. Well, I guess technically speaking, here there's two different variables there. But this is just like a simple case that we can go through step by step to see how we do the backward pass. And then we will make it more complicated with a larger batch size and vectors. Okay, so with the backward pass, you start on the right and you move your way left, backwards ordering. And so we always start with the cost or the loss. And by the way, these are the equations that define the forward pass, and they're telling us exactly the functional relationships between all our variables. So these are the things we have to look at to remind ourselves, the details of how we're actually going to do the gradient computations. Okay, so the very first thing to do is DJ DZO. Okay, now so in other words, so here's our script J. We want to take the partial derivative of this with respect to ZO at the point ZO that we computed in the forward pass. Right? So in the forward pass, we started knowing only this stuff, but we did the work to compute each one of these variables in turn, and so now we know them as numbers. So now when I do DJ DZO, I want to take the derivative of this function at the ZO that I computed in the forward pass. Okay, and I'm just going to call that J prime. So J prime just means the derivative of this J function with respect to the first argument evaluated at this ZO that we computed previously. Is that making sense? Okay, so the exact form of this depends on the loss we're using. Like this could be quadratic, could be binary cross entropy. So it just depends on, I can't really say exactly what this is at this moment until we make a decision about the loss. And I'll show you some expressions in a few slides, but this is just some function we can compute. We definitely can compute it. Okay, so now we've actually computed this quantity. So this now is known also as a number. So the next thing is to do DJ DAH. And we know by the discussion of the chain rule, we can do that by multiplying DJ DZO times DZO DAH. So here we have this. Okay, and the point is that one of these things we already computed. So this is This is not something to compute, it's just something we already stored. So the thing we have to compute now is this. We have to figure out what is DZO, DAH. So let me ask, is Thomas Wu here? Okay, what about Wes Water Street? Okay, Wes. So based on the equations here on the right, what would DZO, DAH be? Yes, exactly. So based on this equation, DZO, DAH is just WO. So this is WO. Okay, and now we've computed this. So now the next thing we can do is want to do DJ, DZH. And so now, since I have already computed DJ, DAH, I don't have to concern myself with this ZO here. I can just say that DJ, DZH is DJ, DAH times DAH, DZH. So that's what we have here. Right. And this thing, we computed this, so that is a known quantity. So the new thing to compute at this point is DAH, DZH. So let me ask, is Cheryl Redding here? Okay, what about Jiawei Liang? What about Vedant Karthik? What about Eric Jackson? Okay, Charles Irons? No. Okay, William Huang? Okay. Yang Ziqian Guo, G-U-O. Zujun Bai. You can see I know which ones to call. Justin Scufa. Daniel Singer. Okay, Daniel. So, all right, so yeah, so we were working on this DAH, DZH. So we need to take the derivative of this at ZH, which ZH is something I computed in the forward pass. So if we're using primes to denote derivatives, then how would you express the derivative of AH with respect to ZH? So this is just some function. It could be a sigmoid, it could be a ReLU. We'll just assume it has a derivative called H prime. Yeah. So just H prime, right? Yeah. So it's H sub hidden prime, that derivative evaluated at ZH, which is a known quantity. Okay. And so now we actually know all these derivatives, and we can use them in the final step, which is to compute the gradient with respect to the parameters. So let's handle the output bias. So to compute DJ DBO, we can do DJ DZO times DZO DBO. So that's this equation. We know this has already been computed, so that's a known number. The only thing to compute now is DZO DBO. So we have this equation here. That's a pretty easy one, right? That's just equal to 1. So now we have computed one of these key quantities. Like these are the whole point, is to compute these, which are used for gradient descent or stochastic gradient descent update of that parameter. Okay, so the next one is DJ DWO. So we can compute that by DJ DZO times DZO DWO. This one was already computed before. DZO DWO, we can see that that's going to be AH. And that was also something computed in the forward pass. So you can see why we need to do the forward pass to even be able to do the backward pass. Okay, and then The only remaining parameters are these. So again, we can, because we know dj/dzh, we don't have to worry about those intermediate variables. We can just do dj/dzh times dzh/dbh to get dj/dbh. And so the only new thing is dzh/dbh, which as you can see is going to be 1. And similarly for this, we have just to compute dzh/dwh, which is going to be x. Okay? So that's the basic flow of how we do the backward pass. Is everybody understanding this? Is it kind of making sense? All right, so the forward pass, you start with what you know at the beginning of that gradient iteration. You compute all these other quantities, and then now that you know those, you can work your way backward, and you can compute all the derivatives. And now that you know those derivatives, you can take your next stochastic gradient descent step or update, and then you begin the next iteration where you have, new parameters. You're sampling from some new mini batch quantities, and you just keep repeating this. Okay. All right. Any questions? Okay. Good. Let's move on to slightly more complicated case where we have a batch size that is now greater than 1. So as a result, we have these curly braces, which mean that they all refer to the batch. So these are all several elements in a batch. Now, of course, these parameters, they're still scalars. They're not batch dependent. They're the same parameters for the entire batch. And so here are our new equations. You can see that, there is I indices on a number of the quantities. And then the other thing is that this scalar loss is going to be the sum over the batch. It's looking at all the costs over that batch. So perhaps we could draw maybe modify our drawing a little bit and visualize it like this. So these are the elements in the batch. B elements, sorry, I didn't write that very well. B elements in the batch. Okay. And we'll complete the diagram as we go through it. Okay, so the first thing we want to do is we want to compute each of these scalar derivatives. So it's like dj dzo, which is a scalar, but separately for each one of our batch elements. So we have this equation here. We do the derivative of this respect to ZOI, and that means that the sum will drop away, and we'll have this for the particular I we're looking at, and then when we do the derivative, we get J prime like that. Okay, is it clear why the sum went away? Because we're looking at one particular I, and this is summing over all I, so we only need to concern the I that we are doing the gradient for. Okay, so we have now computed those gradients. Now let's consider that because we have a batch, we also have a collection of variables here. Again, B of them. And now we want to think carefully about how these are connected. So what do you think? Do these have like this kind of connection where they're all mixing together? Or is it more of like a straight line thing? So remember, these are different batch elements. So when you consider the different elements in the batch, does like the first Z out in this batch depend on all the previous hidden activations in the batch?
No.
No, right? Exactly. So that's nice because it means that this, we really have parallel paths here. And we have the same thing over here, parallel paths. Because really, this collection of variables has to do with the batch, and the batch elements are being processed independently. They are not mixing together until you get to the cost. This is the only mixing that happens. They just get summed at the end. Okay, any questions on that? Okay, great. So we have done this one, and so now we know these quantities for all the different I. And so now let's say I choose one of these AHs and I want to do DJ DAHI. Well, you can see that I don't have to use the multivariable chain rule because there's really only one direct path taking me from J to that particular batch element of AH. Okay, so no multivariable chain rule. It actually looks exactly like on the previous page, everything except that now there's a batch index on all the quantities. Okay, so when we look at DZO, DAHI, it's just, the derivative is just WO. Okay, is that making sense? Okay. All right, and then we can also consider these. So let's say I take one of these i's and I want to do DJ, DZH that I. Well, I can skip to this one because I have already computed that gradient, and then I can skip to the end. So I multiply this thing that I just computed with this new quantity that I have to derive, but this is pretty easy. There's no mixing across i's here, and so we just have, let me ask someone else. Let's see, Yang Shen? Yang? No? What about Elena Sun? Ziheng Tan? Okay, yeah, so what do we have for this quantity here? Yes. HH prime evaluated at ZHI, exactly. Okay, great. Okay, so that was relatively straightforward. Anybody have any questions on that? Okay, so now let's consider the derivative with respect to this output bias. So we have to rethink about how this graph is constructed. So we know that the cost depends on all the elements in the batch. But if you look at these equations, like all the different elements, all these ZOIs, they all depend on this single BO, right? So that means that to draw this picture maybe more explicitly, we have something like this. And so now when you look at the connection from this output bias to J, you have this situation where there's really parallel paths, and that's exactly the situation where we have to use the multivariable chain rule. So, so we're going to have to do a sum over the index I that is indexing across this set. So here we have a sum over I. But otherwise, if we just consider each one of the different parallel branches here, it's the same as the previous slide. So like DJ DZOI times DZOI DBO, like this. And for DZOI DBO, that's pretty easy. That's just equal to 1. Okay, so, all right, so this is where we see some added complexity with the batch size. Any questions on this one? Making sense? Okay, great. And then for WO, it's same, essentially the computation graph looks the same. And DZOI DWO is just AHI. Okay. All right, and then the last two follow the same rules, where for the same reason as before, we have this kind of multi-branching, but we have computed like DJ, DZHI, we've computed that, so we just need to multiply it by DZI, H or dBH to get each one of those gradients, and then we sum them up over the different paths. Okay, so we basically have these bottom expressions. This one is xi. Okay, great. Everybody feel like they understand this page? Okay. All right, so now we're going to make things a little more complicated because we're going to add the vector variables in combination with the batches greater than 1. So now what's challenging is that we actually have, we have like nodes a bunch of nodes that are vectors. So maybe what we can do is we can think of this as something like this. Okay, so we have a collection of a collection of B things in the batch, but each of these things is vector valued in general. This ZO is a vector, boldface. So that's basically what we have in this case. So let's start at the beginning. So we're always going to be doing scalar calculus. So we want to look at the scalar partial derivative with respect to the ith row and kth column in this, you could say, matrix of parameters. So I is indexing across the batch, and then K, maybe I'll draw it this way. K is indexing this way. And then I would be indexing that way. Okay, so for each one of those various elements, we need to take the derivative, dj dzo ik. And that is going to, since we're looking at a particular I, it kills the sum. And then we're going to look at this vector valued thing, but we're taking a partial with respect to just one of the entries in this ZO vector. Okay, so this is what we have, and the exact form of this will just depend on the cost that we're using. Okay, so let's move on to the next one. So over here, we also have a collection of vectors. And we know that there is some decoupling, right? We know that these decouple across the batches. But the question is whether within that same batch element you have this mixing happening or not. Okay, so let's take a look at dj dahil. So I'm looking at one of these particular entries here, and I know that I don't have to consider this one or this one because those are different batch elements. But what about these guys? Do I have to consider all the elements in there? So to figure that out, I just need to look at the equations. So does this single entry of AH affect all of the ZOs? So this is the equation that unites them. So what do you think? Let me ask, is Ryan Zhu here? Yeah. What do you think? Based on this equation, does one element of that A vector affect all the elements of the ZO vector?
No, just one term.
Okay, well, let's try to visualize this. So we have a vector ZO, and we have a matrix WO.
Is that COI written on there, bolded?
Yeah, this is bolded,
Yeah.
right? Yeah. So we can kind of draw this out like this. So this is like the WO matrix. This is the AH vector. We're looking at one particular element here. Maybe it's this one. And so what happens when we do this matrix multiply, that element is going to multiply all of the entries in this column, right? And thereby affect all of the entries in the ZO vector. So there is basically multiple paths. So we could, I don't know how to do this, but basically, yes, there is this kind of mixing relationship. For that same batch element, we have stuff going on. So actually, I shouldn't have done it that way. I should have done it this way. So let's say that we're focusing on one particular element here. And then so the kind of structure we're going to see is we're going to branch that single AHI L is going to affect all the elements in that ZOI. And then those guys, as we know, are going to affect J. So now we do have this multivariable chain rule because we have independent paths. And so we need to have a sum across this, which is indexed by K. So here's sum over K. And then we have DJ, DZOIK. So these are all those. And then DZOIK, DHIL. So those are those. Does everybody understand kind of the topology of this, why we're using the multivariable chain rule here? Okay. All right, any questions so far? Okay, so let's figure out this. What is this exactly? So let me ask, let's see, is Bird green here? What about Sirach? Or Sirach? Yeah. So what do you think? Any ideas how we can compute this? Okay, so let's write this out. So so we're focusing on this equation. So let's look at ZO and let's look at this element IK. We can basically think of this. Let me rewrite this a little bit. So we have our matrix vector multiply. So now what we're doing is we're fixing one of these locations, and we're saying how does that location depend on one of these? So, and in particular, I am looking at the kth entry here, and right, because that's K, and then I'm looking at the lth entry here, L. Okay, so do you have any guesses of how, based on this matrix multiply, these guys, these are connected? Okay, yeah, so this is where the linear algebra is important. So remember that we could write this as a summation across the index L. We're going to have WO, and it's going to be row K, column L, times AH, batch I, and summing over L. Okay. So now that you see this equation, is it more clear? So what is this answer now? It's WO, and so there's just one entry here that matters, right? It's just so it's just this one entry. It's the one in the kth row and the lth column. That's the one that's connecting this to this, right? You can also see that from this equation. So yeah, so it's just going to be WOKL. Okay. All right. So yeah. So this is where it's getting more complicated. Question?
Why do we move the sum? Why don't we still sum over L? Because I know we were
Part of it is that, like, we're just looking at the ELF output.
Oh, okay, got it,
Yeah, so it's like we're looking at this particular, we're freezing L, and then we're saying, yeah, right? Okay, any other questions? Okay. Then we have DJ, DZH, IL. So very similar, except, you know, we're kind of bouncing through that node. We've computed all of these now, so we know those. So now the question is, what is the relationship from the Z's to the A's? So is this one over here, does this have the mixing relationship or not? So let me ask this to Zhao Qi Liu, yeah. Yeah, so the question is, do I have like a mixing of all these variables like here, or is it like straight across? Like how are these vectors connected?
I think it has different cases.
You think they're mixing together?
Yeah.
Okay, let's look at the equations though. So this is the equation that relates them,
Oh, I don't know.
right? Yeah, because this function is just operating element-wise on the individual element, like the kth element here is directly connected to the kth element here through this function, but no other mixing. So this actually is a little easier. So here we just have direct connections. And so that makes our work easy. We don't have a multivariable chain rule to consider here. So there's no sum here, and we just have DAH. So this is just going to be the H prime. H prime H evaluated at ZHIL. Okay. Is everybody good with that? All right. And let's just, because we're almost done, let's just consider finally what's happening with these guys. So we want to look at just one of those, the kth element within here. So we're looking at one of these, and we would like to know, does this single guy here affect, okay, first, does this affect all the different batches? Batch elements? Yes, right? Now, does this, if I look at one batch element, based on this equation, does like the second element of BO affect all the elements in ZOI or just the second one? Just the second one, right? Yes, exactly. So there is a nice decoupling this way. So it's coupled across batches. So we have to use the chain rule, the multivariable chain rule summing across the batch, but not across the different K because it's decoupled through this equation. Okay, so when I'm looking at the kth entry in these vectors, this DZOIK equals, or DBOIK is just 1. Okay, and is everybody good with that? Okay, and very last thing to look at, let's consider this matrix of coefficients. And I'm considering 1 here. So this guy, so let's see, we have to look at the kth row and nth column of WO. So the kth row of this matrix only affects the kth element here, right? So there's no coupling across, there's no coupling like that way. But there is a coupling across the batches because this guy affects all the different elements in the batch. So for this one, it's pretty straightforward. I guess you can see that directly from this equation if you want to compute this. That's the equation to look at, right? So does anybody see what the answer is based on that equation? AHIL. Yeah. Good. Okay. And then the bottom two are very similar. Equals 1 and equals xi. Okay, so we're out of time for today. Sorry for going a little bit late. But we can come back to this next time if you have any more questions. All right, see you guys then.